Hello everybody and welcome to another edition of NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 42 and we will be trying to look into the basic characterization techniques which are available for cryogenic electronics and its characterization. So, just to recapitulate, in our previous editions we had looked into CV, we had looked into a heterostructure CV for n type and p type. We had also seen how does it vary with respect to frequency, what is the meaning of frequency dispersion and so on and so forth. We will now look into what is known as a quasi-static CV characteristics, right. We will look into the quasi-static CV region and we will see how it works out. So, there are two types of modeling techniques available, be it cryogenic or at room temperature, and there are two types of our quasi-static capacitance versus voltage characteristics, and we have non-quasi-static capacitance versus voltage characterization, right. Now, all the CV characteristics which we find out, measured CV characteristics, the determining key parameters are some physical and some structural, are as follows. So, if you want to find out and if you do capacitance versus voltage measurement, from here I can find out the oxide thickness CV, I can find out the substrate doping concentration, be it acceptor or donor type, I can find out the threshold voltage of the device and of course the flat band. So, VTH, VFB can be directly visually seen from the CV characteristics, whereas the first two, oxide capacitance and Na and Nd, will require some amount of mathematical manipulation from the observed graph of CV to extract the value of Tox, Na and Nd. So, the right hand side, if you look, is basically a measurement setup for CV, where the blue colored is basically the CV measurement setup, and this is known as a CV meter, which consists of fixed current source, an AC signal which is VAC here, and a variable bias, right. If you apply a voltage across this, the cap stack which you see, the capacitance stack, this is the cap stack, right. This is your capacitance stack. If you look at the cap stack, you apply the potential across its two edges and then try to find out what is the amount of current flowing through the device, and from there try to extract the capacitance value. So, we have used a CV meter, we have also used a gate bias, DC gate bias, and the small signal AC signal, and this is small signal varied from 1 kilohertz to 10 megahertz, and the signal is primarily looks like something like this. This is VAC. So, your VAC is approximately is equal to A times sin omega t, where A is the peak to peak frequency of the input signal. Why do you want to give it? Why do you want to give VG? VG is primarily the DC bias which you give in order to bias the device in accumulation region or in any region where you want to find the capacitance. Superimposed in that with the AC signal which you give here, which is a low frequency or high frequency AC signal. When you work with 1 kilohertz AC signal, it is typically considered to be low frequency, and when you work with 10 megahertz signal, we consider that to be as a high frequency. Now, the meter which you basically find out is the capacitive AC current. So, there are two currents which we generally find out. One is the DC current and another one is basically the capacitive AC current, right. And if you look carefully, the capacitance is calculated by the formula given by this, where I cap is the measured AC current, omega is basically your angular frequency, and VAC is the small AC voltage which you give. Okay. Now, so what you get here from this left hand side measurement principle is that you are able to extract the value of capacitance, which of course is a function of I cap and omega and VAC. VAC is the input voltage of the AC signal, RMS value. Now, look at the omega. Why omega is coming in the denominator, which basically means that if your omega is very high, which means that you are trying to calculate at a very relatively higher frequency, then you will see that the capacitance will actually go down, and the reason is the particles are not able to react to the changing AC signal, and that is the reason it is only the inversion that comes into picture. There are two types of capacitances, but let us look at the first one initially, which is the type of capacitance, and it is known as a small signal differential capacitance here, small signal differential capacitance, and is given by dQg dV, and it is minus times Q sub by dVg. What is Q sub? Is basically the charge in the substrate. Now, why is it negative and why they are equal? I will try to explain that to you. Now let us look this. So two things we are looking, why they are equal. First of all, why dqg dvg is equals to minus times dq sub dvg, and why there is a negative sign. So let us understand in this manner that whenever you, when you apply a AC bias to the gate side of a MOS device, you are not adding any extra charge carriers to be generated. You are only generating extra charge carriers, and the overall charge will always be neutral. So the charge which is there in the oxide layer, the trap layers, the inversion layer must be all equal to the depletion layer, must be all equal to the substrate charge, and that is the reason any change which you do on the gate side with respect to the applied gate voltage should be reflected by the corresponding change in the substrate charge with respect to gate voltage. Why negative? Because if you sum them together you will get 0, right, and that is the reason why you get a negative side. So I was trying to say this something like this, that this implies that dqg dvg plus dq sub dvg is equals to 0, implying that if you do d of dvg, right, qg plus q sub is always equals to 0. And what does it therefore mean? That if you add the value of the gate charge and the depletion charge, this is always a constant value. Its relative values can change, but the addition will always be constant primarily from the charge neutrality condition. So CV curve does what? It essentially captures different operating points and operating regions, right? We already know that it captures accumulation, it captures depletion, it captures inversion, and also not written here, strong inversion, right. It also provides you a brief insight into the surface potential and how the charge is distributed in the device, right, because wherever charge will be higher, you can actually a priori predict that the capacitance there will be also higher to a larger extent, and that is the reason why CV curves are important to study and get the idea. Now let us look at the quasi-static CV curve. The first graph here, part number A, shows you the accumulation region. The MOS capacitor is simply a capacitor with capacitance equals to Cox, right. Whereas part B, if you look, it shows the depletion region, and therefore there are two capacitors in series. One is the oxide capacitance here, which is Cox, and one is depletion capacitance. Therefore 1 by C prime equals to 1 by Cox C depletion. So this is at a DC bias. Now what you do, you go on applying AC signal to the gate side. So let us look at the last bullet. When you apply an AC signal to the gate side, obviously if it is positive in nature, it will actually reverse bias it, and the depletion region will grow on expanding. So that is the reason I say that WDEP expands, and it also contracts at AC frequency, and therefore the AC charge appears at the bottom of the depletion layer as shown in this graph. You see this part, the negative charge, fixed charges are coming here. Why? Because if you apply a negative charge at the top and you push the electrons at the bottom, there will be a layer of PN junction which will generate a depletion region. However, the width of the depletion region will itself change with respect to the applied frequency, right, and the applied frequency will change the variations in the W depletion. When W depletion changes, C depletion will also change. Now on the left hand side, you see that you will have an inversion region, right. So this figure C, which is this one, shows a MOS capacitor in the inversion region. So with large amount of inversion electrons in the N region. So I had a P type substrate, right. I haven't applied any bias on the drain side, and therefore my depletion thickness here and here are exactly the same, and I have an inversion layer of electrons which are available from this end to this end, right. And this is basically quasi-static, which means that why is it quasi-static? Because if I give a small change, it gets reflected onto the C depletion and it gets reflected on the inversion charge, which means that the charge carriers are able to react to the varying values of the AC signal. However, if the AC signal goes very high, the omega value, you won't be able to get it, and that was the more so the reason. If you see, you had this expression that C was inversely proportional to omega, right, and that is the reason we differentiate between a quasi-static and a non-quasi-static CV, but we will stick to the quasi-static CV at this stage. Figure number D, figure number C was when you have a strong inversion. Figure number D is there is an inversion, but because of high frequency there are no charge carrier, large number of charge carriers not available. Right. Now you see what is this AC and DC. So what this DC is primarily is the inversion charge which has been generated by application of a DC bias onto the gate side. So in strong inversion, if the gate voltage is greater than the threshold voltage of the device, there is a large value of the inversion layer found. Why this AC signal? What is the meaning of AC is superimposed on that. If you give an AC signal to get it, this depletion width will go on varying, C depletion will go on varying, right? And that is the reason there will be a variation. If however the depletion width is not able to fulfill or track the capacitance, we define that to be as a non-quasi-static. So let us come to the numerical part of it, and I say that the C depletion is epsilon by W depletion. W depletion is basically my width of the depletion region, and 1 by C will be obviously equals to 1 by C aux plus 1 by C depletion. If you solve it and if you take the value of C depletion, well known factor, I get 1 by C to be equals to this value. And therefore, if my gate voltage is very different from my flat band voltage, then my 1 by C actually becomes smaller and smaller, which effectively means that C becomes larger and larger. At flat band, understand, at flat band what is happening is that Vg equals to VFB. When Vg equals to VFB, this term goes to 0, and therefore 1 by C equals to 1 by C aux, or otherwise this is correct. You see, when you plot C versus B at VFB, the capacitance is actually equals to C aux, and this is the CV, quasi-static CV which we are drawing, right? Why? Because the inversion charge, Q inversion, can respond to the AC signal if the frequency were infinitesimally low, almost like a static case, and that is the reason it is known as quasi-static, which means that it is almost like giving a DC bias, and the DC bias is changing by a small delta amount as the time proceeds forward, and all the electrons which are there, or holes, whichever is the majority current carriers, are able to respond to the change, and that is the reason it is a quasi-static. Whatever we have studied till now is all quasi-static in nature, assuming that they have been doing it. Now you see, this is your accumulation, this side, this was your depletion till this much, and then you have an inversion. We have already studied this to a larger extent, right. So this is the basic idea of a quasi-static CV region. One more thing which you should note here is that if your oxide thickness starts to reduce, then your C aux increases, right, and which means that if all this graph CV is to be replicated at lower C aux, the whole graph will actually shift more towards the higher C aux, right, and you will actually shift to a higher C aux. This is for lower T aux. Lower T aux means that your C aux is higher, and therefore your capacitance shifts to the top. So all these CV characteristics which you see, assuming that they are actually sort of quasi-static in nature, there is proper, what do you say, proper lowering of the flat band voltage. The flat band voltage still remains the same, but if your T aux reduces, what happens is your C aux starts to become higher and higher, and therefore there is almost a vertical shift in the CV characteristics in the quasi-static region of operation. We will now come to gate to channel capacitance for PMOS and NMOS. Now if you look at, so that's what you have plotted is basically gate to channel, right. On the left hand side graph, if you see, this is gate to channel with respect to a gate voltage, and we have plotted for various values of temperature in a sense, and the lower one is basically the Fermi potential Fe, which is this one, right. Fermi potential at, as I told you, at E equals to EF, I will get this whole function to be equals to 1 by 2, right. So so if you take this formula, and if you take E equals to EF, then I get N equals to E as a function of T integral minus infinity to plus infinity. This whole quantity becomes 1 by 2. So this goes outside, I get NE to the base dE. So it is half of the integral of the density of states over a period of time dE, and I will get the total number of electrons available multiplied by Q. Now, so here I am assuming that my Vg is 0.603 or 0.6 volts as such. What it shows to me, if you look carefully at the top graph, that there is a crossover at the threshold voltage. So Vg is considered to my threshold voltage in a sense, right. This is my VTH, and there is a threshold voltage crossover taking place, which means that below this value CGC was actually reducing with increasing temperature. Above this value the CGC actually increases with respect to temperature, correct? And this is because of the fact that your Fermi energy changes in a manner as shown in the diagram below. Since the Fermi changes and since you are multiplying Fermi level, Fermi energy function with the or Fermi Dirac function with the value of NE, the product comes out exactly the same as my Fe varies. Why it varies? That is more important. It varies because f of E is basically the Fermi function, which you already know that its value is equals to 1 by 2 when the energy is equals to the Fermi energy, and all the states above the Fermi energy are empty, all the states at below Fermi energy at 0 Kelvin. As the temperature increases there are variations, and therefore this gives you the value of CGC to a larger extent. As I told to you, this is f of Et is a Fermi Dirac function, EF is the Fermi level, T is the absolute temperature and Kb is the Boltzmann constant, Ne is obviously the density of states, right. We are assuming that the MOSFET inversion layer is basically a 2D structure, 1D and this 1D and 2D. We are not, thickness is assumed to be very, very low. So, I take this length from source to drain and the depth, the W value inside the MOS device. We are also assuming that EC is set to 0, that makes my life easier because the integration becomes much easier in that case. Under such a criteria, the above equation converts to this equation, which is N of EFT equals to KBT into A to D into ln of 1 plus e to the power EF by KBT, where A of 2D is basically a constant depending upon the density of state mass, electron mass. So, this is a constant, right, this is a constant which is I can assume to be almost independent of temperature. So, this is gate to channel CGC is basically change in the inversion charge with respect to the applied gate voltage. Now, please understand one point which I need to point out here is that as you start reducing the temperature, two things happen. Look at this equation from here. This quantity linearly falls down, right. So, temperature 300, 200, 100, 50 and so on and so forth. So, this Kb into T term actually starts to go on reducing to a larger extent. However, please keep in mind that the exponential term actually starts to increase, and within the natural log it is available there, this quantity tends to increase. So, there is a fight between sort of KBT which tries to pull the value of N down, but as your temperature goes down the exponential term goes on increasing and the natural log term which is in the parenthesis goes on increasing, right, and therefore there is a fight between the two. Which wins depends upon the effective value of EF and other quantities. Now, the front gate potential we have seen it already, I am not going to details of this one, sorry. Because of charge conservation we can say that the total gate voltage is not distributed at flat band, surface potential, inversion charge density Qi by Cox and the substrate which is given by psi s by Vb, where VFB is basically my flat band voltage, right, psi s is my surface potential, Qi is the inversion charge which you see, Cox is oxide capacitance, Cb is the bulk capacitance and is given by Cbox. Cbox is the buried oxide dot CSI upon CSI, Cbox plus CSI, because silicon and the box layer are series with respect to each other, and I get Cb equals to Cbox dot CSI upon Cbox plus CSI, and Vb is the back bias voltage which you give. Now, let us enumerate on the PMOS and NMOS, right, and on the PMOS and NMOS CV characteristics to a larger extent. So, we are trying to find out CGC, the gate to channel capacitance, right, and it, as I told you, depends upon the ratio differential of the inversion charge with respect to the gate voltage. So, if you look at this formula here, I can write down this as dqi dvg, and this can be broken into dqi d psi into d psi dvg, right, because I am using potential surface. If you do a small amount of manipulation, I get this as the final sort of expression for CGC, and it depends upon the product of oxide and the inversion capacitance divided by oxide plus bulk plus inversion, right. Okay. Now, if you see the right hand side figure which plots my CGC with respect to gate voltage, on the right hand side it is NMOS, on the left hand side it is PMOS. Let us look at NMOS, that will be easier for you to understand. And this is 300 Kelvin, this one is basically my 300 Kelvin and this is 50 Kelvin, this is 300 and this is 50. We have taken large channel devices, so W is equal to 10 micron and L is also equals to 10 micron. So, my threshold is somewhere here. So, if you go below threshold, as the gate voltage increases, the capacitance tends to increase. Again, very simple and straightforward, because you are increasing the gate voltage, more and more inversion charge will be available, but since the inversion charge density is very small, even a small change in the gate voltage adds a large value of inversion charge, and therefore the capacitance curve is very steep. However, as you cross the threshold voltage, right, the rate of increase obviously reduces, and the reason for reduction is that by this time the number of charge carriers increase so much that even with an increase in the value of VGE, the incremental addition in the inversion charge is very small. I have already given you an example. Say you are adding, say 10 to 10, right? So that's a 100% increase, whereas if you are adding 10 to 100, it's almost a 10% increase. The concept is exactly the same in the right hand side, which is the N type. In the N type, below threshold, since the inversion charge is very low, even a small change in the gate voltage increases the inversion charges to a larger extent. Beyond threshold, the reverse is true, that you are not able to sustain a very large variation in the inversion charge, and therefore there is a 10 to saturation. What is of more important also as a cryogenic engineer is that the capacitance actually, as you shift from 300 to 50K for the same value of the gate voltage, below threshold 50K gives you a much smaller capacitance as compared to that of the 300K, and that is pure simple because the number of charge carriers are low, carrier freeze out has taken place, and the number of charge carriers responsible for forming the inversion layers are low. Beyond capacitance is just a crossover. When you go to inversion layer, in the inversion layer, and as compared to 300 Kelvin, the inversion layer, the number of charge carriers are relatively less. So, the rate of increase is relatively more, and therefore, there is a crossover which is happening somewhere beyond 50K, and that is true even for PMOS. For both PMOS and NMOS, the reasoning is exactly the same, and we are plotting this value of CGC with respect to this thing. Now, the complete expression for CGVS, which I have just now shown to you, depends upon this quantity, and this quantity depends upon the value of Cox and C inversion, right, and you get some value of CGC, gate to channel potential, from here. As I discussed with you, when you discuss this point internally, also keep in mind that post inversion there is a screening effect which comes into picture, right, and the screening effect starts to screen your inversion layer charge with the depletion charge to a larger extent, and that needs to be taken into account when you find the total capacitance of the device at the cryogenic temperature. So, let me recapitulate what we learned till now, and let me give you a brief idea about what we learned. We learned about the whole model which we had based our expression on is basically our quasi-static model, right. It was not a non-quasi-static model, it is quasi-static model. Why quasi-static? Because we are assuming here that it is almost behaving like a DC, but it is an AC signal, which means that the DC bias is being changed slightly as I move forward. That makes the understanding the mechanisms of inversion layer formation much easy, and the charge carriers are able to respond to the change in the applied signal in a frequency. If you increase the frequency drastically high, the charge carriers will not be able to respond, and you will enter into NQS region and non-quasi-static region. In the second phase, we studied into the variations which we saw, and the variation was primarily the capacitance variation with respect to temperature, right. Finally, if we looked into PMOS and NMOS, and that is what the slide is all about, with variation in the temperature, and we saw that one interesting point was there was a crossover at the threshold voltage for NMOS and PMOS, and the rate of increase is there. So, if you want to therefore use NMOSs and PMOS for all practical purposes in the cryogenics, by this study you can know that where you need to bias for sort of, I should say, a minimum variation with respect to temperature, and the idea is to keep it around threshold voltage. If you keep it near threshold voltage, the cost you pay is a reduced current, lower power, but the gain which you get is the dispersion of the capacitance with respect to temperature is almost zero near the threshold voltage, right. That is even true for PMOS as well as for NMOS. Just keep this in mind, we will go to circuit analysis later on, right. So, I think you understood this lecture and you enjoyed it. Till we meet next time, bye.